Your muscles can generate force in two different ways. They can generate force while moving or generate force without moving. And that's what isotonic and isometric contractions are. Isotonic, the muscle moves and makes force. In isometric, it generates force but doesn't move. So let's start with the isotonic contractions. Think about if you were lifting something up. You were maybe exercising, moving, whatever. Take the biceps brachii. This muscle, as it contracts, shortens, which means your forearm is coming up toward your shoulder. It's flexion. That is going to be a concentric movement. Concentric is the muscle is doing work, so generating force, while shortening. It's a type of an isotonic contraction. So isotonic, concentric isotonic that is, generates force while shortening. Now, the other one up here is eccentric. Eccentric isotonic contractions still generate force, but this biceps brachii now, as it's going through extension, the biceps brachii is getting longer. So it's not really contracting, it's getting longer. But instead of just dropping down, you're slowly letting the weight go down, which means this muscle, biceps brachii here, for example, is still doing work. It's still generating some tension as it gets longer. It's not simply relaxing. That's why if you ever work out and anyone's ever kind of helped you figure out how to work out or gone to a trainer or anything, when you're lifting a weight up, exercising, do you go back and forth as fast as you can usually? No, a lot of times in general terms, you are slowly lifting up, slowly letting it back down. That's because both directions, the concentric and eccentric, are doing work. You're still generating force or tension in both ways. And a lot of times, depending on the research you look at, they're saying that the eccentric actually can be more beneficial than the concentric. But that one depends on who you're reading. It goes back and forth sometimes. But regardless, they both are beneficial directions, concentric and eccentric. Both types of isotonic contractions. Key thing is, the weight is being moved. So you're physically creating a movement. In the case of isometric, your muscle is going to generate force, generate tension, but it cannot generate enough tension to move the object or the weight. Let's say you're trying to pick up and do a curl for a 100-pound barbell. Now, some of you might be able to do that, but a lot of people can't. So if you can, up the weight, make it 150, whatever you know is impossible for you to do. Or let's say you're trying to lift up some countertops that are bolted down to the floor. The idea is it's not going to move. You can sit there and try to generate your force. You can try as much as you want. Your muscles generate force, but they can't move that weight. So the weight, the force is not enough to move it. So in isometric contractions, you're still generating force, generating tension, but you're not moving the object, not moving what you're trying to move. Now, there are isometric workout plans. If anyone does those, you've got to be really careful. So say if anyone's going to do those, be very careful. Because you're not moving your muscles. So you're trying as much as you can, and you can actually tear the muscles apart because you're putting so much force and tension without moving. So isometric exercises can be beneficial, but you got to be careful about those. And sure, you've got to be careful about isotonic also. But the isometric can be even more challenging if you don't know what you're doing. If you know what you're doing, have at it, no problem. But if you don't, ask for help, ask for direction, guidance. Great way to learn. So isotonic, isometric. Isotonic is going to move. Isometric generates force but can't move. All right, muscle metabolism. How do you fuel those muscles to move? Because all that muscle movement somehow is being fueled from energy. So obviously you eat, so you ingest the energy, but how do your muscles get it? So energy is required to form cross bridges, to break cross bridges, to actually transport calcium. So pretty much everything the muscle's doing needs energy. So we have to make sure that we fuel those muscles with enough energy to keep them moving, keep them functional. ATP, adenosine triphosphate, is the fuel source. Your muscles will use ATP as the power source. If you're saying, hold on, isn't glucose the power source? Glucose is a power source, but you have to take that glucose, convert it to ATP, then the ATP is what the muscles use. So yes, indirectly glucose is the energy, but directly the muscles use ATP. And you use up these stores really quickly. So how do you regenerate? Creatine phosphate, CP, is one way to regenerate ATP. Anaerobic glycolysis. Anaerobic means without oxygen. Aerobic respiration is with oxygen. The bottom here I put hemoglobin, myoglobin. Hemoglobin is how you carry oxygen throughout your body. But myoglobin is a special protein that is helping to carry inside the muscles. So think of myoglobin as the hemoglobin for your muscles. All right, let's start at the beginning. Creatine phosphate and basic reserves. You use up your initial ATP reserves in your muscles in about 4 to 6 seconds. And think about in the morning. Your alarm goes off. Have you gotten out of bed within those 4 to 6 seconds? Yeah, probably not. Which means you've already used up your reserves by just simply kind of rolling around in bed to start with. And you haven't even gotten out of bed yet. So the first thing to replenish those reserves is going to be CP, or creatine phosphate. Now, the creatine phosphate can produce ATP because you have creatine phosphate here, you have ADP here. You need to basically say, fine, we'll recreate that and make ATP. That's what we can use for our energy source. Well, if you notice, the first half I skipped over, that's ATP plus creatine. That's how you make the creatine phosphate. That's how you replenish it when your muscles are at rest. But we're working right now, we're moving. So we get about 15 seconds more from creatine phosphate. All right, 21 seconds. Your alarm went off. Are you out of bed in 21 seconds? Probably not. That means the rolling over, I don't want to get out, thinking about, you've used up the first 2 reserves of your ATP. So let's go on to the next step. Now we get into the aerobic pathway. This is with oxygen. The aerobic pathway is glycolysis, Krebs cycle, and the electron transport chain all together. All 3 of those are ways that with oxygen present, we can generate ATP. So starting off in the cell, but outside the mitochondria, you have your glucose from your blood, no problem. That glucose, which is right there, is going to go through the glycolysis process. Through glycolysis, you'll generate 2 ATP molecules and 2 pyruvate molecules. Now, we're not going through all the steps of that. That's not necessary for right now. But no, glycolysis takes that glucose and makes 2 ATP and 2 pyruvate. As long as you have the oxygen present, or again, aerobic, you then come down here and take that blood glucose, which we just did, and it goes into make the pyruvates, take the pyruvates, and then go into the mitochondria. That then is the Krebs cycle, as well as the electron transport chain. So in that case, what you're doing then is making a whole lot more ATP. That's this. We're looking at upwards of about 36 ATP per glucose molecule when you're in the aerobic respiration. So the whole series here. So when you have oxygen present, it's pretty efficient. 1 glucose, about 36 ATP. That's a lot of energy to use. But that's in aerobic. In anaerobic glycolysis, so this means you don't have enough oxygen now. And this usually occurs when you've reached about 70% of your maximum force for a muscle. So if you're really exercising hard, working hard, doing something where you're really losing enough energy and your muscles generate a lot of tension, If you're at that 70% tension mark, 80%, 90%, or even maximum, at that point, your muscles will shift into anaerobic glycolysis. That's because as the muscles shorten, they bulge, they get thicker, pinching all the blood vessels inside. So if you pinch the blood vessels, you reduce your oxygen content to your muscles. So you're saying, well, that's not really great. No, it happens. It's okay. Your body can compensate. But as the oxygen is impaired, it can only compensate for so long. So here we're going to have now that glucose went to pyruvic acid, same as before. We still have the glucose heading in, making ATP, making pyruvate, no problems. The difference now is, though, a lack of oxygen. That lack of oxygen is making lactic acid. So that lactic acid, besides the 2-ATP, is the end product. You stop. You don't go any further. There's no more steps. This is it. 1 glucose became 2-ATP and lactic acid. Not really very efficient, especially since that lactic acid, as it builds up, starts to create kind of like a burning sensation in the muscles. If you ever had an extremely hard workout or working for long periods and you feel like kind of burning the muscles at the end, that's the lactic acid. It's not as efficient because it can't be taken and converted into the Krebs cycle or electron transport chain. So we're only getting a 1-to-2 ratio here, 1 glucose, 2 ATP. Where if you were back in the aerobic respiration, 1 glucose to about 36 ATP. And we also have to regenerate our oxygen debt. So it doesn't matter if we're in the anaerobic or aerobic states. If you're using a lot of ATP, you're still basically have to kind of repay things back at the end. Anaerobic obviously repays more at the end because you didn't have it for a period of time. What this is doing is the oxygen debt. It's basically you must replenish all of your oxygen reserves. So what that means is you have to rebuild or replace what you've used. First thing that happens, lactic acid is converted back to pyruvic acid. Well, if you go back to pyruvic acid, you can then go through the rest of the respiratory pathway there. Go through the Krebs cycle, go through the electron transport chain. So get that burning sensation out of there, which is not good, and then start to reuse it. Then we're replacing the glycogen stores. Glycogen is just glucose molecules forming a large molecule for storage. So one glycogen molecule will have dozens, if not hundreds, of glucose molecules together. Because if you think about it, when you're exercising, you're not necessarily eating the whole time. So you have to pull this glucose from someplace. You're pulling it from the reserves. And you must replenish ATP. You must replenish creatine phosphate. Basically replenishing and putting those back to where they were. So your oxygen debt, replaying it as you rebuild. The idea is when you stop at an exercise routine or you're out sprinting or running or something, you're breathing really heavy. That heavy breathing is trying to replace the oxygen back to where it was. You're trying to replace and repay the oxygen debt. You're repaying that debt as long as your breathing is higher. Once you're back to a steady state breathing, you're almost repaid, but you've got a little more kind of finishing up to do yet. So the muscles, looking at a little bit of how metabolism works, how you generate energy in your muscles, and how they move.